Let's talk about something pretty mind-blowing. In the world of particle physics, scientists have just found a whole new universe of information, but not where they expected. Not in the giant collisions they were looking for, but in the near misses that everyone else's computers were literally programmed to throw away.
For the longest time, the main game plan in particle physics has been pretty simple, if a little brute force. You take some particles, you ramp them up to incredible speeds, and you ask the big question, what happens when you just smash them together?
Right, and the answer is usually this massive, chaotic spray of subatomic bits and pieces for scientists to sort through. But what if the real secret, the revolutionary new tool, wasn't in that smash, but in the miss? Well, that's exactly where this story gets really, really interesting.
Okay, so to really get why a miss could be so unbelievably important, we need to take a quick step back and talk about the very fabric of reality. We have to look at the force that holds basically everything you see, everything you are together. We're talking about the universe's invisible glue.
They call this the strong force, and it's one of the fundamental rules of nature. It's carried by these tiny particles called gluons, which act like a kind of cosmic superglue, holding the protons and neutrons inside an atom's nucleus together. Seriously, understanding them is the key to understanding, well, pretty much everything.
So how in the world do you even start to study a force like that? Well, you're going to need a pretty epic piece of machinery. You need the world's biggest, baddest smashing machine.
And this is it, the Large Hadron Collider. You've probably heard of it as the LHC. It's this massive 27-kilometer underground ring where atoms are sped up to just shy of the speed of light and then slammed into each other, head-on. For years, the goal has always been to analyze that chaotic shower of subatomic fragments to figure out what matter is really, truly made of. But here's the twist. Buried in the absolute mountains of data from this very machine, a team led by MIT did something different. They decided to look at the events everyone else was automatically filtering out, the stuff they all considered noise. And hidden deep inside that noise, they found a revolutionary new signal. And you've got to hear how the lead author Gian Michele Innocenti put it. He said for years, these near-miss events, what they call photonuclear events, were just annoying background interference. But his team realized this so-called noise was actually a brand new, super clean way to see inside the atom.
The difference in approach here is it's everything. Think about it. Direct collisions are brute force. It's like taking a sledgehammer to a watch to see how it works. You just get a messy shower of parts. But these near misses, they act like a precision tool, like a surgeon's scalpel, using a tiny pinprick of light to probe the nucleus with incredible accuracy. Whatever one thought was noise is now the main event.
I mean, this is a huge shift in thinking. The team effectively turned the world's biggest particle smasher into its most precise microscope. It's a completely new way of using this incredible machine.
So how does this new microscope actually work? It all comes down to a phenomenon that sounds like it's straight out of science fiction. It's basically a quantum flashlight.
All right, so picture this. As two particles are racing toward each other at almost the speed of light, their powerful energy fields get squashed flat into these weird pancaked halos. These flattened halos then start spitting out incredibly high-energy photons, which are literally particles of light. In a near miss, a single photon from one particle's halo just zips over and pings the nucleus of the other one. It's not a smash, it's more like a quantum tap. And this gentle little ping of light is just powerful enough to do something amazing. It kicks out a very, very special kind of particle, one that acts as a perfectly clean messenger from deep inside the nucleus. And that messenger particle is called the D0 meson. What makes it special is that it contains something called a charm quark, which is super rare and isn't found in normal, everyday matter. This makes it an unbelievably clean probe. When your detector sees one, you know exactly where it came from and what caused it. There's just no confusion.
So just how rare are we talking here? To find this signal, the team had to sift through data from tens of billions of collisions just to find a few hundred of these perfect D0 meson-producing near misses. I mean, that's not a needle in a haystack. That's a specific needle in a continent-sized haystack.
So, they found the needle. Awesome. But why does this new tool, this new way of seeing, actually matter so much? Well, because for the first time, it's allowing us to peek at the universe's fundamental blueprint in a way we never ever could before.
And here's where it all connects. The energy and the path of that D0 messenger tells scientists exactly how the gluons, that invisible glue we talked about, are distributed and how they're behaving inside the nucleus. It's like a direct measurement of the strong force itself.
So what are they finding? As Innocenti says, when you squeeze matter together this tightly, the gluons start behaving in a funny way. They are quite literally discovering new behaviors for the most powerful force in the known universe. This is rewriting the rulebook.
All right, so let's just wrap this up. What's the big takeaway here? We now have a completely new kind of microscope to study the strong force. It uses a quantum flashlight of photons from these near misses to get an unbelievably clean look at gluons, the very glue of our universe. It's a fundamental new tool for understanding the rules that hold everything, and I mean everything, together.
For years, this incredible, revolutionary signal was just dismissed as noise. It was hiding in plain sight in the very data that everyone was systematically programmed to throw away. It really just makes you wonder, what else have we been missing?